This video will cover Section 1.1. You will not need to complete the Section 1.1 exploration because you've already done an example without knowing it. Section 1.1 allows you to dip your toe in the data analysis pool. We start by introducing the basic ideas needed to answer a research question without the terminology you will need to use later. And actually, we've already done this. Remember day 1 in the class when we wanted to see if we as a class could read Martian? Look back over that activity. We will use it to review Section 1.1 in this video. The research question from day 1 was, can we read Martian? And to collect data, we asked each student which symbol was Bumba, and then we recorded if the student was correct or not. Our result, or statistic, was the proportion or number correct for the class. What were the observational units? You, each student, was an observational unit because you are who we collected data from. And what variable did we collect? Is it categorical or quantitative? Well, from each student, we recorded if the student was correct or not, so that is our variable. Correct or not puts students into categories, so it is a categorical variable. As with any data collected, there are two possible explanations for the results obtained: random chance, or something else is going on. For this study, that would mean students were guessing randomly which one was Bumba. Your book would refer to this as the chance model, or chance explanation. Or students had a reason for choosing which one was Bumba. We can read Martian, or some other explanation. One way to analyze data is to use simulation. We simulate what should happen if we were to repeat the study many times, assuming one of the two explanations is true. But which explanation should we simulate? It is far simpler to simulate the chance model, as you are only simulating one option. In this case, that the proportion of students who correctly identify Bumba is 0.5, instead of having to simulate lots of possibilities, that the proportion is 0.51, 0.52, 0.6, 0.92. So that's what we did. We simulated what we would expect to see if the class was just guessing. The final and most important part of analyzing data is to compare what actually happened to the simulation. In other words, comparing our class's data to the 1,000 simulated classes, which we assumed were guessing randomly. Let's make sure we can connect the aspects of the real study to what we did in simulation. We flipped a coin to represent one student stating which symbol was Bumba. Heads, if you recall, was that the student was incorrect, and tails represented that the student was correct. The chance of heads was 0.5, as with any coin flip. This represented the probability of correctly identifying Bumba by chance alone. And one repetition in this study would be one set of, say, 40 simulated students, or one simulated class. Your class may have had fewer or more than 40 students in it, but for this example, let's pretend that our class had 40 students. The 3S strategy is something we will follow repeatedly throughout the semester. I would highly recommend having this in your notes. The first S stands for statistic, or we will compute the statistic from the observed data. The statistic for Martian alphabet was your class's result. How many students, or what proportion of students in your class correctly identified Bumba? The second S stands for simulate. Identify a model that represents a chance explanation. Repeatedly simulate values of the statistic. Remember, the number or proportion of your class which would correctly identify Bumba. That could have happened when the chance model is true, and form a distribution. The final S is strength of evidence. Consider whether the value of the observed statistic, our class's result, is unlikely to occur when the chance model is true. What would it look like if the observed statistic is unlikely to occur when the chance model is true? it would mean the observed statistic is in the tail of the distribution you create by assuming the chance model. If the observed statistic is in the center of the simulated chance model distribution, that would say the result is likely to occur under the chance explanation. You will see lots of examples in this course of data that is statistically significant. That is the result of what is known as publication bias, where studies with significant results are more likely to get published than those without. First, let's think about what it means in research if the results are statistically significant. A result is said to be statistically significant if it is unlikely to occur by chance alone. So, if the observed statistic is far in the tail of the distribution simulated assuming random chance, that result would be called statistically significant. What does that tell you about the chance model? That it does not explain the data and is unlikely to be true, leading us, the researcher, to believe the second explanation is correct, that something else is going on. That is when we get to say something about the world we live in. But what if the results of research are not statistically significant? What does that tell you? If our observed result does fall in the center of the chance model distribution, what would it say? Well, certainly the chance model could explain the results of the data. But does that mean the chance model is necessarily the only explanation? Let's pretend 24 out of 40 students in a class correctly identified Bumba. Do you know for sure that exactly 50% of all students can identify Bumba? Could it really be 55%? 24 out of 40 is 0.6, so maybe it's really 60%. All three of these values, 50, 55, and 60, as the percentage of all students who would correctly identify Bumba, are all plausible explanation for the result 24 out of 40. And there are many other values as well. Results that are not significant do not tell us that the random chance model is correct. They only tell us that the chance model is a believable or reasonable explanation for the data, but certainly not the only plausible explanation. A more familiar context, and an easy example of that is the criminal justice system. We assume in the U.S. that a defendant is innocent until proven guilty. We assume the defendant is innocent, and the prosecution has to collect evidence to try to prove the defendant is guilty. Similarly, we assume our chance model is true, and we collect data and calculate a sample proportion to try to prove that the chance model is incorrect. If the data, our evidence, contradicts the chance model that someone's innocent, we will convict them. We believe something else is going on. If the data, our evidence, could have come from the chance model, we acquit the person. Note, we still never find someone innocent. We just say that they are not guilty, or we do not have enough evidence of their guilt. Some final terminology before we head into Section 1.2, the deep end of the statistical language pool. A parameter is a value which summarizes some characteristic of a population. From Martian alphabet, the parameter was the proportion of all students who correctly identify Bumba. The key word here is all. It tells us we are talking about a population. We could also use the word population, in other words, the proportion of students in the population who correctly identify Bumba. Or we could use the words true or long run, which also indicate population values in statistics. In other words, we could say the true proportion of students who correctly identify Bumba, or the long run proportion of students who correctly identify Bumba as our parameter for this study. Some key points. Parameters are typically unknown. We don't have data from all students, so we don't know the proportion of all students who will correctly identify Bumba. But parameters are fixed. They don't change. It holds for an entire population. A statistic is an estimate of a parameter. It is a value which summarizes some characteristic of a sample. From Martian alphabet, our statistic was the proportion of students in our class that correctly identified Bumba. We wrote this value down in number 9, part A of the Martian alphabet activity. We can calculate statistics. They will always be a number from our data, but they will vary from one sample to another. In other words, if we looked at a different class of 40 students, do you think we would get exactly the same number of students who correctly identify Bumba? Probably not. So the statistic would be different for this second sample or for this second class.